Welcome to the Explainer. Today, we're diving into a force that, well, it holds atoms together, it powers our technology, and it can even make a balloon stick to a wall. It is an invisible force that literally shapes our entire world. Right, this classic party trick. The answer lies in that invisible force, and together, we're gonna demystify it. It's not magic, not at all, it's just physics. So let's start at the very beginning. To really understand this so-called magic, we first need to meet the hero of our story, the electric charge. This is the core concept, the main character that makes everything else we're about to discuss possible.
So here's the deal. All matter, everything you can see and touch, is made of atoms. And atoms have positive protons and negative electrons. Now, usually they're perfectly balanced, but when that balance gets disturbed, that's when an object becomes charged.
And what's really cool is how charge comes in two flavors, positive and negative. And it all comes down to the movement of just one tiny particle, the electron. See, if an object loses some electrons, it's left with more protons than electrons, giving it a positive charge. But if it grabs some extra electrons, it gets a negative charge. It's that simple. And these two flavors, they live by one simple, absolutely unbreakable rule. Positive repels positive, negative repels negative. But positive and negative, they are drawn to each other. This is the foundation of, well, everything in electrostatics. Okay, so this brings us to our first little puzzle. If charges have to be unlike to attract, how can a charged object, like a ruler you've just rubbed on your hair, attract something totally neutral, like a scrap of paper? The secret has a great name, electrostatic induction. The charged ruler doesn't even have to touch the paper. Just its presence, its electric field, forces the charges inside that neutral paper to separate. The paper's positive charges kind of scooch closer to the negative ruler, while its negative charges get pushed to the far side. And because the attraction is happening over a shorter distance than the repulsion, attraction wins out. And this quote just nails it, doesn't it? It shows how fundamental principle of physics can feel like everyday magic. What you're really doing is manipulating this invisible world of charges all around us. Okay, now that we get induction, let's zoom out a bit and look at the fundamental rules that govern all charge behavior. I mean, everything from a balloon on a wall to a bolt of lightning is dictated by these three core properties. These are the non-negotiable laws of the electrostatic universe. All right, these are the official rules. Additivity just means you can add charges up like regular numbers. Simple enough. Conservation, though, is huge. It means the total amount of charge in a closed system never, ever changes. But it's this third one, quantization, that is truly fascinating.
Now, this last one, quantization, is a little mind-bending. It means you can't just have any amount of charge you want. It has to come in specific, identical, block-like units. Think of it like money. You know, you can have 1 cent, or 2 cents, or $1, but you can't have half a cent. Charge works exactly the same way.
And that smallest little cent of charge, it has a specific value. This ridiculously tiny number you see right here. This is the elementary charge. The crucial point is that all charge in the universe is just a collection of these tiny packets. You can transfer one of them, or 2, or 1 billion, but never, ever 1.5. So we know how charges behave. But how do we measure the actual force between them? You know, how strong is that push or that pull? Well, lucky for us, there's an equation for that. And this whole relationship is summed up by a really elegant and powerful rule called Coulomb's law. It perfectly captures something we all kind of feel intuitively. Distance matters. A lot. The formula shows us the force is directly proportional to how much charge you have. You know, more charge equals more force. But, and this is the critical part, it's inversely proportional to the square of the distance. That little r squared is the key. It means if you double the distance between two charges, the force between them doesn't just get cut in half. It drops to 1/4 of what it was. It's one of nature's favorite rules, actually. Gravity works this way, too. You know, once you understand these basics, it opens up a whole universe of new questions. It just makes you see the world in a completely different way. These simple rules we've covered, they lead to some pretty profound implications. This question really makes you think about charge on a planetary scale. That immense charge isn't being created or destroyed. It's just being massively redistributed between the clouds and the ground. It's the law of conservation of charge, just in its most dramatic and spectacular form. This is such a great question because it's all about balance. Your body contains an absolutely astronomical number of positive and negative charges, but they are so perfectly, so precisely balanced that overall you stay electrically neutral.
And finally, this simple law of repulsion we learned points to the existence of an even more powerful force. I mean, Coulomb's law tells us that the nucleus of an atom packed with positive protons should fly apart instantly. The fact that it doesn't is the proof that another force, the strong nuclear force, is at play, which, well, that just leaves us with a whole new mystery to explore.